Hello folks, here we are again. Same shirt, same hat, same books behind me. Today we're going to talk about graph analysis. Going to do this two different ways. This video is going to be on it from a kind of a mathy point of view. Second video will be considerably shorter. It'll be on kind of a seat of the pants approach. Anyway, stay with me.
Here you have an arbitrary function. There are three ways you can take information from this. The most mundane is to simply take data straight off the graph. So let's say it's a position versus time graph, and you decide you want to know what's happening at t equal to 4 seconds. You go down to the graph, you go across, lo and behold, apparently the body's at minus 6 meters relative to the origin. The second thing you can do is to look at the slope of the function and the way that the slope changes. So let's make this into a position versus time graph. I've decided I want to look to see what the slope is at t equal to 10 seconds. Determining the rise over the run of a line that's changing, that's not linear, is not an easy thing to do. So what is normally done is you draw a tangent to the line at the point of interest, and then you figure out what the rise over the run of the tangent is, and that will give you the slope of the line at the point of interest. So in this particular case, delta y was 4 and delta t was 4, and apparently the slope at that point was 1. You will notice that with this position versus time graph, the slope's units are meters per second. Meters per second are the units for velocity, and in fact the slope of a position versus time graph is going to end up giving you instantaneous velocity. As a minor side point, if this had been a velocity versus time graph, the units of the rise would have been meters per second, of the run would have been seconds, the overall units would have been meters per second per second. The slope of a velocity versus time graph is going to give you an acceleration. So we're going to go back to a position versus time graph and take a look at the way that the slope changes from point to point. So at this point right here, you have a negative slope, which suggests a negative velocity. At this point, you have zero slope, which is to say zero velocity. At this point, you have a positive slope. At this point, you have a positive slope whose magnitude is even bigger. And so basically what you have going through this section is velocities that are changing from point to point to point to point to point to point, which suggests that through this section you have an acceleration. Along this section here, the slope at this point, and this point, and this point, and this point, for all intents and purposes, is pretty much the same slope, which means the velocity is pretty much the same, which means there is no acceleration along this line, or at least not much anyway. So the bottom line is that by looking at the way that the slope changes from point to point, you can tell whether or not there's an acceleration happening in the system. Third thing you can do is not very useful for position versus time graph, but if you happen to have a velocity versus time graph or an acceleration versus time graph, looking at the area under the curve can be quite useful. So I'm going to assume I have a velocity versus time graph, and I'm going to additionally assume I have an object that's moving at 8 meters per second. 8 meters per second essentially means that every second the body's going to move 8 meters. So if you go for 4 seconds, that's going to end up being 32 net meters that the body will displace. I'm going to pick a 4-second interval. Any old 4-second interval will do. I just happen to pick this particular one right here, and I'd like to look to see what the area under our function is over that interval. This is looking like a rectangle. Area under of a rectangle is the height times the width. The height happens to be 8 with the units of meters per second. The width is 4 with the units of seconds. You multiply the two together to get what the net area is here, and lo and behold, you end up with 32 units. The seconds cancel out. You get the units of meters. This is the number that we came up with originally that is effectively the displacement of the body over that 4-second period. So the conclusion that we can draw is that if you have a velocity versus time graph, the area under the curve, the area under the velocity versus time graph, is going to give you the net position change, the net displacement over that time interval. If it happened to have been an acceleration versus time graph, it would have given you the net velocity change over that time interval. So what happens if you've got a function that is partially in the negative region and partially in the positive region? How do you deal with that? We have to look at that. So let's take another look at this function that we've been messing with. And let's assume that we're looking at a velocity versus time graph. And additionally, let's take a look at what's happening between 8 seconds and 16 seconds. So between 8 seconds and 13 seconds, the velocity is going to end up being negative, which means the body is moving in the negative direction, which means the displacement will be negative, which means the area under the curve is going to give you a negative number. From 13 seconds to 16 seconds, the body is transited into velocity that's positive, so it's turned around. It's now moving in the positive direction, which means the displacement is going to end up being positive. When you add the two together, you will either get a positive number corresponding to a positive displacement or a negative number corresponding to a negative displacement. So this is the function that you had for homework. I'm going to treat it like a position versus time graph and see what we can make out of the motion of the body, assuming that was the case. Along here, you can see that the body's position is at -8 meters relative to the origin. The slope of the graph is 0, which tells you that the velocity is 0 along that section, which means it's sitting still. It transits from having no velocity to having some velocity, which means that through this section right here there's an acceleration because the velocity is changed. Along this section you have a positive slope, which means that you have a positive velocity. The velocity does not change along this section, which means the acceleration is 0. The body passes through the origin at t equal to what, 10 seconds? It proceeds on up in here till about what, about 15 seconds. It transits from having some velocity to having no velocity, because along this section the tangent is 0, the slope is 0, so there's no velocity, which means through this section here you have an acceleration. And the body ends up sitting still at y equal 8 meters. So this is a more formal presentation of what I just said. And your homework assignment is to treat this function as though it were a velocity versus time graph and see if you can't make sense out of the motion, and then treat it as though it were an acceleration versus time graph and see if you can't make sense out of the motion. Anyway, have fun.